Greetings! In this video we'll talk about something called the change of basis with an example. Let's consider for this example, and we're not going to do it in general, or we're not going to do a proof or so on, or let's say we might take it into more abstract terms in another one, but in this one we'll really do an example of it. So let's consider the vector space R2 set of real valued vectors that have two components inside. Now let's say that the change of basis is basically a method for us to understand the transition between using one base to describe every element inside this vector space to another base. So we know a base, the most elementary base for R2 would be 1, 0 and 0, 1. We can generate any real vector using linear combination, real valued such vector of the vector space using a linear combination of these two basis vectors. In the case of change of basis, nevertheless, it's taking into account the fact that for the same vector space we can have more bases that actually we can take the various linear combinations of to gain the same vector. So we have to also count with different linear combinations for different bases. That's what happens. So let's consider this case. Let's say we have R2 and we have some two bases, and the bases are namely B that will contain the vector 1, 0 and the vector 1, minus 1. Alright, and then we have another basis which is also linearly independent, but it has slightly different vectors. The vectors here are slightly different. And so what we want to do is we want to consider the idea that we have some vector in the vector space, and we can represent it either using basis B or using basis C, and we want to see like a transition between these two ways. So let's say the concrete example we will use in this case will be our vector 3, 4. So our vector 3, 4, how would we represent it using this basis? Well, we can solve a linear system, we can create the matrix, augmented matrix, and solve it, or we can try to do it without that method. We can just try to combine these two vectors in a linear combination. Just think about it. So what could work? What actually ends up working is we can do 7 times 1, 0 minus 4 times the second one, 1 minus 1. So just to check it, 7 minus 4, that's the 3, and 7 minus 4 times minus plus 4 times 0 plus 4 is the 4 right here. So our option here is, if we want to take a linear combination of these vectors to make it the vector 3, 4 in this vector space, we need the weight 7 for the first vector and minus 4 for the second one. And now what we want to play with is basically the way in which we will be able to, if we know that in terms of the basis B, it will have basically the vector 7 and minus 4. That means that for this basis can be also written as a matrix, by the way, and it's a very important fact here. So how we could also write out this thing is we can do this. 1, 0, 1, minus 1, and then multiplied by this vector that we just found, which are the two weights that we use for these two vectors of the basis. That is 7 and minus 4. And what this will do is it will tell us what coefficients to use for the two vectors of the basis in order to get 3 and 4. As long as we're considering this particular basis. As you see, the vectors in basis C are different, they have different values, so the weights 7 and minus 4 will no longer work. But just to expand it in the usual way, you expand a matrix with a vector, multiplication is going to give this. Again, so we just get back to what we had here. And just to verify, yes, indeed, it goes to 3, 4. So the point here is that if we write the two basis vectors as columns of the matrix and then multiply by the vector that we constructed by taking the two coefficients that we need as weights for the base vectors to construct this particular member of the R2 vector space, then we can also consider a particular way in which we can transfer from B to C. Because we see that we will no longer use 7 to the minus 4. And how does this work? Well, namely how it works is we will express B1 and B2. Let's consider that, let's say that these two bases have these two components each and they're called in a particular way. And let's say for basis B, these two vectors are called B1 and B2. We will refer to them as that. And these will be in basis C, so they will be called C1 and C2. And what I want to do is something called a change of basis, and we will denote it as B arrow to C. What this will mean, it will be basically a matrix that will allow us to transfer from that vector that gave us the weights to express the 3, 4 in B, to give us the weights to express that same thing using these two, using the base C, using these two, not these two, but these two. And how will we construct it? Well, the point here is that we'll again eventually create a matrix. And how will we create it? Well, we want to first express the new basis C in terms of, or in other way, to express the old basis B's components in terms of the basis C. So what I want to do is, I want to write B1 as a linear combination of the C's vectors, and B2 also as a linear combination of the C's vectors. So how will I write B1 in terms of C? Well, B1 is 1, 0. So 1, 0 will equal to a linear combination of C1 and C2. How many C1s and C2 we have to add together to get 1, 0? Well, we can do this. We can do C2 minus C1. Because if I subtract C1 from C2, I get 1, 0. That's what I mean. And in a vector way, I can write it like this: minus 1 and 2, because this is coefficient for C1, that's here, it's actually switched order now, and C2 is coefficient, no, it's just minus 1 and 1, because it's minus 1 and 1 is the coefficient for C2, like this, C1, C2. So this is the way to express B1 in terms of the basis vectors of C. So one of the basis vectors of B in the terms of the basis vectors of C. And B2 is namely 1 minus 1. How to express it in terms of the basis vectors, again, of C? Again, I will look at it and try to figure out. So in this case, it ends up being C2 minus 2C1. We have 1, 1 minus, for this one is 0 times 2, for this is 2 minus 2 times 1. So we have 1 minus 1 like that. We can verify it, or we can just write out the coefficients right here. So again, for C1, which is the first component, is minus 2 here. In this vector, we collect the weights. C2 will be 1. And again, to just signify, we're doing it in terms of C1, C2. This is why I multiply it also by the vector C1, C2. This denotes a dot product. This is the same thing, because the dot product, what it does is multiplies the like components and then adds them. So this is what is here, but now we made it more clear, put it into this vector matrix 2 by 1 matrix notation, column vector notation. And so how does this work? Well, we actually got to the very result of this at this point, because all we have to do to get the change of basis that we were talking about earlier, this SB to C, because the change of matrix will be change of basis will be a matrix, is to take these two things. In other words, the vectors that took us from B1 and B2 respectively into C, and put them as columns of this SB to C matrix. So this matrix will be, just take these two vectors here. So minus 1 and 1, and minus 2, 1. So this matrix, so it equals. So this matrix is the change of basis from B to C. And what it means is that we found out, now I consider example, let's say F, and this is an important piece of notation. Let's say F belongs to R2, by the way. So it's a vector in the vector space R2. And I want to express it in terms of B. So this, if I put it in these in these square brackets and I put the subscript b, it means that I express the vector b as a linear combination of the vector f as a linear combination as just an arbitrary name I chose. It could have been x, for example. I express it as a linear combination of the members of the base b. So what is that? Well, it is namely, it's what I did before with the equation, how I write it in this dot product notation again. I can write it out in a second again. And what it was, it ended up being actually 7 and minus 4. And why it was so? It was because f, and by the way, to specify, what I mean by f is the vector that we considered some time ago. So in the beginning, I talked about some vector 3, 4. Just this vector belongs to R2. And this is, for our example, the vector I'm using. So what we have here is, we have this basis, b, and I'm able to express 3, 4 in terms of the basis b in this way. Why does it work out so? It's because if I do 7b1 minus 4b2, it equals to, just plug in there, 7 times 1, 0, minus 4 times 1 minus 1. And what it gives is 7 minus 4 up there, and below we have 4. So it's 3, 4. So the vector 3, 4 in terms of the basis b is given by these two coefficients, and therefore b1, b2, this unit reference vector to the members of the basis via their names b1, b2 is dot producted with the coefficients, with the weights we apply to them. And now what I want to do, I know 7 and minus 4 is f expressed using the basis b. And what our change of basis does, and I've written this many times just to make it clear, is it transfers our expression from in terms of basis b into in terms of basis c. And all we have to do here is just recognize that we had 7 minus 4. So 7 minus 4 was in terms of the basis b, and to get the vector f, but not now in terms of b, but in terms of c, in terms of the base c, all we have to do is take this 7 minus 4. That means, take this vector 7 minus 4 that we found that it's in terms of b, and multiply it by the change of basis matrix b to c. And I plug in there. We have 7 minus 4 times minus 1, minus 2, 1, 1. And again, I multiply by 7 in the first column, plus minus 4 times the second column. So we have this, and the result will be minus 7 plus 8, and 7 minus 4. So this should be 1 and 3. So what this tells us is that if we want to express 3, 4 in terms of c, then it must be 1, 3. It must no longer be 7 and minus 4. It must be 1, 3. And we can prove it here, just to check. We don't really have to check if we believe it, but we can numerically check it. And that means what I will do is C1, C2 times this new 1, 3 we got should equal to the 3, 4. Will it be so? We take the two parts. So it's C1, I can write it as a dot product. Actually, I can algebraically expand it. So C1 plus 3C2, and that should be equal to 0, 1 plus 3 times 1, 1. And that equals to 3, 4. So indeed, we checked it. And what this all says is that this vector 3, 4 in R2 can either be expressed using B, and then it will be 7 and minus 4 applied to B1 times 7 and B2 times minus 4, or in C it will be, and hopefully this is still in the view, and in case it is not, I will just write it once more here. 3, 4, 3, 4, I will just modify, but it will be 1, 3 in case you want to use the base C. Because if I do 1 and 3, that means 1 times C1 plus 3 times C2, it will also get 3, 4. And the main point of the video was this change of basis, which is this matrix we obtained when we expressed B1 and B2 individually in terms of the vectors of the second new base. And then that give us these two column vectors, and we put them in the matrix together. And this matrix we multiplied the coefficients in the case of B by in order to obtain the vector we needed for C.